Welcome to Study Loop.
So now we'll work on problem 122 from chapter 17. This problem asks us to calculate the pH at several different points. One half, the beginning of the titration, one half the equivalence point, and 5 milliliters beyond the equivalence point. And so we should sketch the titration curve and pick a suitable indicator. So first, we are told this is based on the problem 121 where we were titrating ascorbic acid. So for ascorbic acid, the Ka1 for ascorbic acid is equal to 8.0 times 10 to the minus 5. And so the pKa would be equal to 4.10. Now, ascorbic acid has two deprotonation steps, but the second one is a very, very weak acid, and it only tells us to consider one equivalence point. So we're going to take 5 milliliters beyond the equivalence point as being 5 milliliters beyond the first equivalence point. So now we need to calculate the moles of acid that is present in solution. So we have 0.552 grams. This is all from the previous problem, 121, divided by the molar mass of vitamin C, ascorbic acid. And that's equal to 0.0031, 0.020 moles. We'll draw a generic formula here for ascorbic acid, and then we're told the volume is 20 milliliters. So if we want to get concentration, we go 0.00313 divided by 0.02 liters, and this is equal to 0.16 molarity. So first, let's calculate the pH when no base has been added. And that's 0 milliliters. So we need to draw an ice table since we have a weak acid. So H2A plus H2O produces HA minus plus H3O plus. So initial change in equilibrium. So we have 0.16 initially here, none over here, minus X, plus X for our products. And so we can set these terms equal to Ka1, which is 8.0 times 10 to the minus 5. And we get X is equal to 3.58 times 10 to the minus 3. And then we can convert this to pH by taking the negative log and getting 2.45. So this is our initial value of the pH in this titration. So next it asks us to look at the equivalence point. So we can look at the equivalence point next. And for the equivalence point, all of the acid, ascorbic acid, has been converted to the conjugate base. So we can draw our equilibrium here as being HA minus plus H2O produces A2 minus, now the conjugate base. And so we need to calculate the initial concentration of HA minus. So this can be done first by calculating the volume of base that we need. So we have we know the number of moles that we need. And if we divide by concentration of base, we get the volume of acid base that is used. So 28.4 is the equivalence point, and then we consider that we had a 20 milliliter sample at the beginning, so the total volume is now 48.4, and we divide 0.013, this number of moles, by 0.0484, and we get 0.065 is our concentration initial for the conjugate base, which is now the acid. And so we subtract x, add x, and we use the K KB since we're producing H3O here. So we're going to use the pKa2, the second pKa, which is equal to, or the second Ka, which is equal to, or the pKa is equal to 11.8. So the Ka is equal to 1.58 times 10 to the minus 12. Which is equal to x squared over 0.065 minus x. And so we have x is equal to, if we multiply by 0.065 and then take the square root, we get x is equal to 3.21 times 10 to the minus 7. And so if we take the negative log of this value, we get our pH at the equivalence point is equal to 6.49 pH units. So that's at the equivalence point. Now at the half equivalence point, we already calculated the volume of equivalence. So the volume will be equal to 28.4 divided by 2, which is equal to 14.2 milliliters. And then the pH will be equal to the pKa because the moles of base and acid are equivalent, so therefore it should be equal to 4.10. Now the last step that they ask us to do here is to calculate 5 milliliters beyond the equivalence point. So we can calculate the moles of base that we have, 5 milliliters, or the moles of excess base that we have, if we only take into account 5 milliliters. So we get 0.005 times the concentration is equal to 5.52 times 10 to the minus 4 moles. Now this is excess sodium hydroxide, so this will react completely with the conjugate base, which is also an acid. So because it's a diprotic acid, it will continue reacting with the conjugate base, which is now the acid. So the moles of HA minus that remain is going to equal to what was there at equivalence, which is all of the ascorbic acid species, minus this 0.000552, which is 5.52 times 10 to the minus 4. And we get 0.00258 moles. And then the moles of A2 minus will simply equal the moles of excess sodium hydroxide. And so we can calculate the pH using the Henderson-Hasselbalch equation. Here we're using pKa2 because we're in this second step. And we get the log of base over acid, so 0.000552 over 0.00258 is equal to 11.80 plus negative 0.67 is equal to 11.13. So now we can plot this titration curve. So we'll first draw our axes as straight as possible. And so on the bottom, we're going to have volume of base on the x-axis, and then pH on the y. And we're going to go up to about 40 milliliters, or let's draw up to 40 as our scale. And so we can put 20, 10, 30, 7, so once again, if you've drawn these before, you know if you're drawing by hand, it's not going to be perfect. But let's go ahead and check each point that we have. So initially we counted at 0 milliliters, the pH was 2.45. So we can draw that a little above halfway around here, between 0 and 4. Then for the second point that we had at the equivalence point, we said that the pH was 6.49, and this occurred at 28.4 milliliters. So at 28.4 milliliters, the pH was around 6.49, so about here. Then at half the equivalence point, we had pH of 4.1 at a volume of 14, so roughly here. And at 5 milliliters beyond, so 28, 33.4 milliliters, we had a pH of 11.13, so about here. So those are the 4 points we sketched. We can draw in our graph an initial increase, a sharper increase at the beginning. And then we have a sharp increase here, decrease there. So the line is not as straight as it should be, but this is the rough shape we have for the titration. Further on, let me go ahead and erase the point above what we calculated because there will be a second equivalence point somewhere up there. And it should be around, based on the first equivalence for it was 28.4, so it should be around 56.8 milliliters, but that's further up. And the last part that it asks us is to look for a pH. So based on the fact that the pKa is equal to 4.1 for pKa1, a good indicator would be bromocresol green if we look at table 17.1